All righty, lads and ladies, welcome back to Calc 1 and congratulations on surviving your first exam. We are cruising into the middle part of this course now, which is where we're going to stop worrying so much about the mechanics of taking derivatives and start seeing what we can do with them. This is a fun part of the class, especially if you have an interest in physics or any of those, kind of industrial revolution era things that really changed the world. F equals ma is the backbone of the Industrial Revolution, and this is where we learn the mathematics that allowed all of that to happen. So we're going to begin today by learning about implicit differentiation, excuse me, which is going to allow us to take derivatives of a handful of functions we haven't differentiated in the past. But more importantly, it's going to allow us to attack a class of problems called related rates problems, which are truly physics things. I will do my best to keep us focused on the mathematics and not get too sidetracked by the physics, but it is the nature of this stuff that word problems are the best way to express and explore the mathematical ideas. So today is just implicit differentiation, but I want you to be aware that where we're going with this is a place that will have a large number of word problems. So yeah, let's get to it. Really quick, before we dive in here, if you did not take exam 1 on Monday, for any reason, really doesn't matter. If you were sick, that's fine. If you had a flat tire or your dog got arrested, that's fine. It doesn't really matter to me why you didn't take it if you just didn't feel like doing it. If you didn't take exam 1 on Monday for whatever reason, please come to my office hours this Friday. That's when I'm holding the makeup session. And I will get you into the makeup test. The makeup test is not the same test, but it is very similar. It's not any harder or any easier. It's just slightly different. A number of people did reach out to me, and that's wonderful. I'm glad that you feel comfortable enough letting me know where you're at, and just try to be mindful that we're moving into new material. You don't want to fall behind on that new material just because you postponed the first test. So here we go. This is MAC2311. The section number is 004. This is a Calc 1 class, and the date today is the 9th of February 2022. Unfortunately, I have we all got COVID. So one of my son's, classmates at daycare was COVID positive last week, and it followed him home, and now we're all sick as shit. So if I'm not my normal sharp self, I apologize. It's a very strange thing, though, like brain fog that comes with this. So, oh, good question. Yeah, Jas, are the homework grades going to be imported into Canvas anytime soon? As a general rule, do not do that mid-semester. So if you look in the grade book in Canvas, I'm not going to do it now because it will show everybody's grades. But if you look in the grade book in Canvas, you have the opportunity to enter a what if score there. So just take your total percentage in WebAssign, whatever that says, and multiply, write that as a decimal, multiply by 45, and you can enter that to see what your overall grade in the class will look like with the homework added in. You can also approximate, right? If you know you've done like 90% of the homework problems, you take 45 and multiply by 0.9 and put that in as your what if score. But generally, no, I don't enter the homework grades in the Canvas gradebook until the very end of the term because those change every time you access WebAssign. And there's no way for me to get it to import automatically on a day-to-day basis. But if you're nervous about your grades, you want to see where you're at, and the grade computation is like daunting or whatever, feel free to come by an office hour and we can do that together just so you know exactly where you are. Because I do want you to know exactly where you are at any given time. So today, let me pull up your syllabus. I can give you a even clearer picture of where we're going. Here. So we just finished exam 1. And today we're talking about, like I said, implicit differentiation, which is going to allow us to take derivatives of a handful of new functions. And it's also the main tool that we're going to use down here in related rates. And related rates is one of those sections that I think usually takes a little bit more effort to get it to click. Between those, we're going to talk about log derivatives. This is this section could easily be a part of implicit differentiation. It doesn't really need to be its own thing. But that's where we are and where we're going. After that, we're going to talk about linear approximation, and really everything from here down to exam 2 is all applications of the derivative, stuff that you can do with the derivative. So today, we're talking about implicit differentiation, which I think is section 3.5. The word implicit is an antonym for the word explicit. Explicit means, what's a synonym for explicit? Given exactly, right? So an implicit expression is something like, I'll just use an example that we're all familiar with, something like x squared plus y squared equals 1. It's not solved for either variable. If I solve this for y, we get, well, let me do it here, x squared plus y squared equals 1. I can subtract the x squared from both sides, and I get y squared equals 1 minus x squared. And then I can take square roots, and I would get y equals plus or minus the square root of 1 minus x squared. This y equals the square root of 1 minus x squared, or y equals negative square root of 1 minus x squared, are explicit expressions. Basically, the idea is implicit comes from the word imply, right? I-M-P-L-Y. You can kind of see the root of the word in there. This equation implies both of these equations. So we would say that this is an implicit expression, and the implicit expression implies these two explicit expressions. What we want to do is get y primed, or dy dx. We want to get the derivative of y with respect to x out of the implicit expression rather than solving for y and then taking the derivative. And there's a bunch of reasons to do this. First, the mechanics of differentiating an expression like x squared plus y squared equals 1 are relatively simple. It's all power rule stuff, and there's going to be a bit of chain rule involved here that I'll explain in a little bit. The mechanics of differentiating either of these is quite nasty. Yes, there's power rule, and yes, there's chain rule, but it's like nastier chain rule, right? I would, just looking at this is like a polynomial equals a constant. I would rather differentiate polynomials than big, gnarly radical expressions. So one of the advantages to the thing we're talking about today, implicit differentiation, is that it's going to allow you to solve tangent line problems in the context where your expression isn't solved for y. You'll be able to cook up the tangent line. Does anybody know what this implicit expression's graph looks like in the xy plane?
Isn't it a circle?
Yeah, not just any circle, it's the unit circle. It's the circle centered at 0, 0, whose radius is the square root of 1, which is 1. Let's hop over to Desmos for a minute and try to convince you that, oh, no, that's not what you need. Convince you that those pair of equations at the bottom are equivalent to the implicit expression we began with. So here's x squared plus y squared equals 1. If you take that general equation for a circle, like x minus h squared plus y minus k squared equals r squared, plug in 0, 0, and 1 for h, k, and r, you get this. The blue is the positive square root, y equals square root of 1 minus x squared. And the negative square root gives you the lower semicircle. And together, they form the full circle. The idea is that this thing, if you try to solve this for y, you get this plus and minus when you take the square root, right? When you take square roots on both sides, just like x squared equals 4 gives you x equals 2 and x equals negative 2. When you take that square root, you get a plus and minus. Kind of what's going on here is that this thing is not a function, right? This fails the vertical line test. It's not a function. It does not represent y as a function of x globally, but it does represent y as a function of x locally. If I just pay attention to some part of that, this little limited part of the curve does pass the vertical line test if I ignore everything else. So while we cannot regard y as a function everywhere here all at once, I can say that this equation implicitly defines y as a function of x in a region of any point. Now there's a catch there. If you come over here or over here, there is no region, like no chunk of this curve that contains this point where y is a function of x, because you'll have some little part that fails the vertical line test. So you got to stay away from these points where the tangent line is vertical in order to say that. But as long as you're comfortable with that, as long as you're comfortable saying, okay, for the most part, this defines y as a function of x. Explicitly, those functions could be written this way. Then there is no harm in just thinking about this expression defining y as a function of x all on its own. And we never need to talk about these explicit expressions. We can stay here in implicit land. Now, what the fuck am I even saying? In terms of mathematical notation, what we mean when I say x squared plus y squared equals 1, implicitly, COVID brain fog, implicitly defines y as a function of x is that we can assume changes in x in that expression correspond to changes in y. So in other words, if you plugged in a particular number for x here, you could always solve for y. That's all. That's all. If you plug in a particular number for x, I trust that from this expression, after plugging in any particular value for x, I could then solve for y. And it may be the case that I'll get 2 y values out. In any given situation, I'll say I only care about one of them, right? This would be written saying y equals y of x, right? So in this expression, we can assume that y is really a function of x. And you could write that as y equals f of x or y equals y of x, or you could just leave it alone. Just write y as y. but with the understanding that I'm not thinking of x and y as separate independent variables. I'm thinking of x as the independent variable, and I'm imagining that y changes along with x. There's a very important theorem in analysis, which is like the grown-up version of calculus called the implicit function theorem, that says if you have any expression like this, no matter how cattywampus and fucked up it is, you can always, at least in theory, solve for y. Maybe not globally, right? Like here, we don't get a single global solution for y, I get two separate solutions. But in the neighborhood of any point, you can solve for y in a way that is meaningful and correct. And that would tell you that y really is a function of x. All right, this is all well and good. Why do I care about this? Well, because I know how to differentiate composite functions. So if y here in this expression is really f of x, then this is like x squared plus f of x all squared equals 1. And you could differentiate on both sides and then try to solve for f primed. Let me try it. This gives us a new way to find y prime. All right. Which would be f primed of x. I'm going to start off here using this notation because it's the closest to what we're familiar with. But as we practice and get a little bit more comfortable, I'm going to just stick to writing y prime. So let's do it. First, let's go ahead and say x squared plus y squared equals 1 by the implicit function theorem is x squared plus f of x all squared equals 1. This is where the chain rule is going to come in. I want to find f primed. And this little apparatus here is a composite function. I've got an inner and an outer. So differentiating I'm going to apply the operator ddx to both sides. The right-hand side is easy, ddx of 1, that's 0. 1 is a constant no matter how you look at it. On the left-hand side, ddx of x squared, that's not hard, that's 2x. And if I differentiate f of x all squared using the chain rule, I get 2 f of x times f primed of x. And this is an implicit expression for the derivative, which I could then solve, right? Just trying to isolate f primed. This is equivalent to, I'll subtract the 2x over, I get 2 f of x times f primed of x equals negative 2x. Divide both sides by 2f of x, you get f primed of x is equal to, the 2's will cancel. You'll have x over f of x, negative x over f of x. And then remember, f of x, that's y. F primed, that's y primed. So this says y primed is negative x over y. So it's a new way to find y primed. That's what this is. If you assume that y is positive, I can say now, recall, y is either the square root of 1 minus x squared or the negative square root of 1 minus x squared. So if we assume that y is positive, this thing says that y prime is negative x over the square root of 1 minus x squared. Bump it up. Now let's compare this to what we would have gotten if we differentiated from one of the explicit expressions. So if I take, again, under that same assumption that y is positive, the positive square root of 1 minus x squared, and I differentiate on both sides, then I'd get y prime, because, let me write this, this is 1 minus x squared all to the 1/2 power. If I differentiate this explicit formula, then I'd get 1/2 times 1 minus x squared to the negative 1/2 times the derivative of the inside here, which is, well, I'll just write it. How about that? 1 minus x squared primed. I'll go too fast. This is by the chain rule. This would be 1/2 times 1 minus x squared to the negative 1/2 times negative 2x. And you can cancel the 2's. And you get negative x. And then this guy is downstairs the square root of 1 minus x squared, which is the same thing. So this provides a new path to get the derivative. The beautiful thing about the first approach is that not only did I not have to solve for y, it wouldn't matter if I even knew how to solve for y. So if that was a more complicated thing than x squared plus y squared equals 1, something where I could not solve for y, and there are many expressions like that, I could still have jumped in and used the implicit differentiation technique to get a formula for my derivative. Now, as I did it up here, the implicit differentiation felt like it took a little while, but it was the first time you saw it. And in order to kind of help you feel comfortable, I used some extra notation where I wrote f of x in place of y everywhere. We don't need to do that. So first, any questions on what we did here or the mechanics of what we did above, getting us to this? Okay. So again, in the step above, everywhere there is a y, I treated it like f of x. So y squared got treated like f of x all squared. And then when I differentiated, this is kind of the magic step here. And it was a chain rule. Here's the big idea. To differentiate expressions with both x and y with respect to x, treat y like f of x. That is, use the chain rule. And the fact that ddx of y would be ddx of f of x. It wouldn't be 1. The ddx derivative of y is not 1. It's like ddx of f of x, which would be f primed of x or y primed. This might seem silly or obvious. If it does, that's good. That means that you're understanding. Let's try a crisp example. Find the equation of the tangent line to our unit circle, x squared plus y squared equals 1 at the point root 2 over 2, comma, root 2 over 2. As always, we know we need a point and a slope. We've been given the point explicitly, which is nice. The slope comes from the derivative. Well, what derivative? It comes from dy dx, or y primed. So what I need to do is differentiate this thing to find y primed. And I'm going to do it again. I know it's the third time, but I'm going to do it again. This time I'm going to do it in the style and notation that I want you to do as you solve implicit differentiation problems. So to find this, the point we already have, to find the slope, we need y primed. And we need y primed at this point. To get y primed, I will apply the operator ddx to both sides of this equation. And you really do want to write the ddx on both sides, like a ddx with parentheses around the whole equation is sloppy. And as I differentiate on the left-hand side, I'm going to use the big idea above, that I can apply the chain rule and remember that the regular ddx derivative of y is not 1, but y primed. So ddx of x squared is 2x plus ddx of y squared is 2y, that's the derivative of the outer, leaving the inner alone, times y primed. ddx of 1 is 0. It's the same thing that we did before where I wrote f of x and f primed in place of y and y primed. I'm just not using that cumbersome notation because it is implied that y is a function of x, hence the name implicit differentiation. Even better, I have no obligation to solve this for y prime. I can if I want to, but I don't have to. I could just plug in this x and this y and solve for y prime. Let's do it like that. So at our point, this becomes 2x. Well, x at this point is root 2 over 2 plus 2y. Y at that point is also root 2 over 2 times y prime equals 0. Cancel schmancel, cancel schmancel. You get root 2 plus root 2y prime equals 0. So root 2 y prime is negative root 2, subtracting this root 2 over. And now dividing both sides by root 2, you get y prime is negative 1. So y primed at our point, at the point we need it, is negative 1. And now you've got a point and a slope. You're done. You just got to write down the answer. Therefore, our tangent line is y minus y0 equals our slope m, negative 1, times x minus x0. And that really is it. Yes, you can distribute and solve for y if you want here, but you don't need to. That's job done. And I'm going to verify in Desmos in just a minute, but I'll give you a second to write. So when you're doing implicit differentiation, when you're differentiating with respect to x, and you get to a piece that involves y, you kind of differentiate like normal and then multiply by y primed. And what I'd like you to see or understand is that that really is just the chain rule. If instead of y here, I wrote f of x, then differentiating f of x all squared, we saw before just a minute ago, you get 2 f of x to the 1 times f primed of x by the chain rule. This is precisely the same thing. It's just a more convenient notation. And it allows you to solve these otherwise quite cumbersome problems very, very quickly. Any question on the differentiation here? Okay, let me convince you in Desmos that we did the right thing. So without ever thinking about an explicit solution, without ever writing down f of x, we were able to come up with y minus square root 2 over 2 equals negative 1 times x minus square root 2 over 2. There she is. And this is indeed the tangent line at that point. Looking awful tangenty to me. So among other things, implicit differentiation is a shortcut to finding y primed in expressions like this, where you never have to solve this for y. Can you solve this for y? Yes. Do you need to? No. Are there lots of things like this that you cannot solve for y? Yes. Like if I had xy plus the natural log of y equals 1. Can't be done. You cannot solve that explicitly for y. There are many, many, many expressions out there. You just start writing down random combinations of algebraic, objects involving the variables x and y. Odds are, the random thing you write down, it's literally not possible to solve explicitly for y, meaning you have just y and then just stuff with x's on the other side. Let's take a look at one more example, and then we're going to differentiate inverse trig functions using this. I'll grab one from your book here. Yeah, this is the vibe. Of course, you can write dy dx instead of y primed if you want. Something a little more raucous. Yeah. How about this guy? This is good. Now, so let's find y prime in the expression sine of x plus y equals y squared cos of x. Good luck solving that for y. I'm just going to copy this down. I want to address the obvious question first. Well, what if I tried to solve this for y? Is there any way it could be done? If you wanted to start that, you've got a y here and you've got a y here. To get the y out of the sine function, you would have to take the inverse sine of both sides. That would get you a y here. You subtract the x over, and then you'd have y equals the inverse sine of y squared cos x minus x. So by solving for this y, you would trap this y inside of an arc sine. And conversely, if you try to solve for this y by dividing both sides by cos of x and then taking square roots, you would have this y still stuck inside under a square root inside the sine function. This cannot be solved for y. It's impossible. All right? That's just how it is. There's lots of stuff like that. But can I get y primed? Yeah, if I differentiate implicitly. So we apply d dx to both sides. And differentiate implicitly. And remember that implicitly just means that I can assume, at least locally, that y is a function of x. Need not be true everywhere, but at most points along this curve, this does define a curve. At most points along this curve, if you just look at a little window around that point, that graph will pass the vertical line test. Let's take I haven't actually seen this curve before, so let's take a look at it before we do this. That'll be fun. Holy strange shit, Batman. All right. So definitely not a function, right? Does not define y as a function of x globally. But if I zoom in and I just look at some portion of it, I just look at like this portion here, or any one little portion, that little portion does pass the vertical line test. All right. If I do it, I get d dx applied to sine of x plus y equals d dx applied to y squared times cos x. On the left-hand side, you will need some chain rule. On the right-hand side, you will need product and chain rule. The chain rule on the right-hand side comes from the y squared. The chain rule on the left is obvious. Your sine is your outer, x plus y is your inner. do the left-hand side first. If I differentiate here, I differentiate the outer function, leaving the inside alone. And then I need to multiply this by the derivative of x plus y. And remember, the derivative of y, the ddx derivative of y is not 1, it's y primed. So this would be 1 plus y primed. Is everybody okay with what I've done on the left-hand side? Okay. On the right-hand side, product rule. The ddx derivative of y squared is 2y times y primed. This is the derivative of the outer, leaving the inside alone, multiplied by the derivative of the inner. Remember, y is not just a variable, it's a function. So the derivative of the inner is y primed. We leave cos x alone. And then we add to that what we get when we leave the y squared alone and differentiate cos x. That's negative sine of x. So this is the expression we get by differentiating implicitly on both sides. Solve for y prime. We can clean it up a little bit first. I'll distribute over here. I'll write the y primed in front of the cos of x plus y because it looks better. On the right-hand side, I'll have 2y cos of x times y primed. I'll write it like that. I don't know. How about 2y y prime cos x? That's fine. Either way is fine. Whatever you like. And then minus y squared sine of x. Maybe you remember from pre-calculus classes how to solve an equation like this for a particular variable. I've got a y prime here. I've got a y prime here. I don't have y primes here or here. So I'm going to take every term that has the y prime in it to one side, and every term that doesn't have a y prime in it to the other side. So let's see, if I want things to look pretty, I'm gonna put all the y prime stuff on the right and all the non-y prime stuff on the left. So that means I'm going to subtract this term over to the right, and I'm going to add this term over to the left. The other two pieces will stay where they are. So on my left-hand side, I'll have the cosine of x plus y. I'm going to subtract this piece over, plus y squared times the sine of x. And on the right-hand side, I'll have my 2y y prime cosine of x minus y prime cosine of x plus y.
Can you hear me?
Yes.
One equation up where you were starting to simplify. Yeah, that the second term in the y prime cos x plus y. Where did you get that?
So I'm taking the cos of x plus y and I'm distributing this across it.
Oh, okay. Sorry.
No, it's okay. Plus this times y prime, and then I put the
Okay.
y prime out front.
Thank you.
It's a little bit complicated looking, right? One of the fun parts about this class, go practice at the library or in the classroom, put the stuff on a whiteboard. People walk by and they'll just drool or get scared or run away crying. It's fun. So from there, our goal is solve for y prime. That's what they said, find y prime. I'm going to take everything with the y prime, put it on one side, everything without a y prime, put it on the other side. We do that because our plan is to factor out the y prime and then divide over by whatever's left. It's just like finding the inverse of a rational function. So y prime here, that's a common factor between these two terms here and here. So I can factor the y prime out on the right. I'll leave the left-hand side alone. when I pull out my y prime here, I'll have 2y cosine of x minus the cosine of x plus y. And now the bracketed expression, I can divide both sides by to get y prime alone. So it's a big, scary looking thing. But God himself can't stop you from doing it. It's all kosher algebra. Boom. There it is. You want y prime? Here's y prime. So in our first example, the idea was, well, we could have attacked it either way. I could have solved for y and then taken the derivative using all the normal tricks. Here, there's no way in hell to solve the original thing for y. So if you want y prime, this is your only option. It's really not that bad. The only step where we did something new is here. And the only thing we really did is apply the chain rule when we differentiated the pieces with y's. But it takes a bit of time to understand why it's the chain rule. And if you're ever uncertain or lost, you can just write f of x instead of y, f of x all squared instead of y. And then it will look precisely like those chain rule problems. Remember the square root of 5 plus 2f of x or whatever we differentiated last time? Same shit. Same shit. That was really implicit differentiation. I just didn't tell you. So you already know how to do this. It's just a new notation. Is there any step here we'd like to look at a little bit more closely?